In this video, we're going to go cover part 1 of section 8.3. 8.3 is kind of a large section, so I'm going to break this up into two videos. 8.3 is on polar form of complex numbers and de Moivre's theorem. So really we're just going to deal with polar form of complex numbers in this video, and we'll do de Moivre's theorem in part 2. So our first question here says to graph the complex number 2 minus 3i. So I just want to graph that complex number, and this is pretty straightforward. To graph a complex number along what is normally your x-axis is going to be your real axis, which we denote with an RE. The y-axis is the imaginary axis, which we can denote with an IM. So to graph the complex number 2 minus 3i, we travel a positive 2, right? Because we travel in the real line. 2 is our real value, our real part. So we travel on the real line, positive 2. Negative 3 is our imaginary part. So we travel along the imaginary line down negative 3. And we go 2, comma, negative 3. And that plots our point 2 minus 3i in the imaginary plane. So, or in the complex plane. I shouldn't say the imaginary plane, the complex plane. So we've drawn a point, a complex number in the complex plane. We want to carry on here and do this part 2. Part 2 says to write the complex number z equal to 2 plus 2 square root of 3i in polar form. I'd like to point out that z in polar form should be written as z is equal to r, where r is some radius, times cosine of theta plus I sine of theta. So what we need to find is r and theta for this value up here. Now, how do we do that? It might be best to draw a picture first here. Let's draw 2 plus 2 square root of 3i. So we got 1, 2 units. I'm going to go ahead and add in a fourth here. And this is the real line. Oh. And then we're going to go up 1, 2, 3, 4 here. 2 square roots of 3. Square root of 3 is 1.7 approximately, so 2 times that is approximately 3.4. So 2 up and about 3, or 2 over and about 3.4 up gives us 2 plus 2 root 3i. Now, if we draw a right triangle here, what we have is a triangle with side length 2 and with side length 2 square roots of 3 here. And really we're trying to find the polar form of this point. So to do that, the first thing we do is we first calculate the modulus. Now, what in the world is the modulus? The modulus is the radius r, which is the same as the magnitude of the complex number z. And what is the magnitude, or what is the length of that complex number z? It's the same as this radius. So what is the radius from here to here? Well, that is the hypotenuse of this right triangle. So to find that, we find the Pythagorean theorem, or we do the Pythagorean theorem. So this is really the square root of a squared plus b squared. In our particular problem, this says that r is equal to the square root of 2 squared plus 2 square roots of 3 squared. And then this is the square root of 4 plus 2 square roots of 3 squared is 4 times 3. This is the square root of 16, which is 4. So our modulus is 4, or the radius here is 4, which I can put back up here now, right in the that part of the triangle. We also know that tangent of theta is equal to b over a. Well, b is the opposite side, right? So we have theta here. V is the opposite side. And so that is 2 square root of 3. And we divide by the adjacent side, which was 2, so we get square root of 3. And then to find theta, we do tan inverse of square root of 3. That's equal to theta. And we know then that pi over 3 is equal to theta. This tells us that z is equal to 4 times cosine of the angle theta, which is pi over 3, plus I sine of pi over 3. And that's our polar form of the complex number 2 plus 2 square roots of 3i. If we go back up to this triangle, this tells us, by the way, that theta is pi over 3. It's what we just calculated just a moment ago with this tangent of theta. So, again, z is equal to 4 times cosine of pi over 3 plus I sine of pi over 3 is the polar form of 2 plus 2 square roots of 3i. I would like to note that z is equal to 4 times, let's go ahead and find out what cosine of pi over 3 is. Well, cosine of pi over 3 is 1/2. And sine of pi over 3 is the square root of 3 over 2. If we go ahead and distribute our 4 here, 4 times 1/2 is 2. 4 times the square root of 3 over 2 is 2 square roots of 3, and then that was multiplied by I. So again, if we just calculate out 4 times cosine of pi over 3 plus I sine of pi over 3, we do in fact get 2 plus 2 square root of 3i. So these are the same. We just, in this problem, our goal was to start here and work backwards to get to that polar form. All right. We have one more question on this video. And then, again, the next video will deal with de Moivre's theorem for 8.3. So in this last question, we want to write the product of z1, z2, and the quotient z1 over z2 in polar form. And we're given z1 and z2 here. z1 is the square root of 3 times cosine of 80 degrees plus I sine of 80 degrees. z2 is 4 square roots of 3 times cosine of 70 degrees plus I sine of 70 degrees. So as we have just seen, we can write complex numbers in polar form like this. So if we have two complex numbers and we need to multiply them and they're already in polar form, we can see how to do that here with this problem. So for the first part here, part A, where we do the product, z1 times z2 is equal to r1 times r2 times cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And so for our problem, z1 times z2 is r1 times r2. Well, that was square root of 3 times 4 square root of 3. And then cosine of theta 1 was 80 degrees. Theta 2 is 70 degrees. So this is equal to 4 times the square root of 3 times the square root of 3. Square root of 3 times the square root of 3 is just 3, so 4 times 3 is 12. Times cosine of 150 degrees plus I sine of 150 degrees. Okay, so that is z1 times z2. We also want to do z1 divided by z2. And the formula for that, which is also in your book, is r1 over r2 times cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. All right, so this is square root of 3 over 4 square roots of 3 times cosine of 80 degrees minus 70 degrees plus I sine of 80 degrees minus 70 degrees. So this is equal to 1 over 4 times cosine of 10 degrees plus I sine of 10 degrees. Not too complicated if we know the formula, and the formula can be found in your book. You'll want to know those two for this section. And that's it for this first video on section 8.3. Tune into the next video for de Moivre's theorem.